Okay, good morning, everyone. It's a great pleasure to be here at this fantastic event and to talk about the future of computing. And I come from IBM Research, and I'm leading the Science and Technology Department in Rüschlikon. So for me, we are all very busy in quantum computing, as Sergey already mentioned, but for me, it's just a quick early ride in the morning to come here. So let's have a look back. When we talk about the future of computing, we should also look back a bit and see what has happened over the last 70 years. And a lot of technology has been developed, starting from the first integrated circuit, which were kind of two transistors glued together, soldered together in a very simple manner. Then to 1971, where you had the first integrated circuit with 2,300 transistors. And then further on developed high sophistication, lithography going down in dimensions, Moore's law, where we could establish a transistor, an integrated circuit in 14 nanometer FinFET technology, 24 cores, so not only one, but multi-core, with more than 8 billion transistors, high sophistication. And all this has led to tremendous use of technology, which we all have in our pockets or on our watches, etc. So improvements in cost, performance, power, and functionality has led to the technology which we have available today. And if you look at this conventional CMOS technology which is used for these computers, then there are also limits. The number of transistors is still continuously increasing, as you see here. So a lot of engineers are making this possible. However, you also see that certain things are leveling off here. And this is, for example, the frequency. The frequency scaling has actually stopped about 12 years ago. So the frequency of the integrated circuits is running at the same frequency because of energy problems. Otherwise, our technology would melt away. The typical power also has matured because this is about 100 watts, 200 watts. That's what we can cool with the technology which we have available. That's a limit also for the frequency. The number of logical cores has increased because this was a solution to the frequency scaling, saying, okay, we take more cores. And the question is, however, what is coming next? Because transistors, what we are using today, are based on bits. That's what has been mentioned already. And these bits are today kind of processed with these transistor technology. So starting in the range of millimeters, now we are at the range of nanometers. And so the new transistor technology which we are using for the 5 nanometer technology is shown here. And what you see is actually here, these stacked are the channels where the current is flowing through. And around here you find the gate which shuts the current off and on, so which creates the 0 or the 1 which you need for the computation. And these dimensions are about 5 nanometer in height and 12 nanometer in distance, in width. And going smaller is more and more complicated also because of the physics. So shutting off these transistors is becoming more and more complicated. And so this geometry of having the gate completely wrapped around the transistor is the ideal geometry in order to switch on and off the current. And it's not clear what this 3 nanometer node will be. And so this is really kind of the ultimately scaled silicon technology. And the question is really what's coming next. And however, today we can make sophisticated devices and processors and machines and systems, and not only the small ones which you know and which you use in your mobile phones and your iPads, etc., but also very big computers. And this is an example of the world's most powerful high-performance computer, so-called Summit. And this computer can do about 200 quadrillion calculations per second, 200 petaflops. It has 4,600 nodes, more than 9,000 IBM Power CPUs, and more than 27,000 NVIDIA GPUs, 250 petabyte of storage, and it consumes about 15 megawatt. So that's the biggest machine, and it can do enormous calculations. And if you look at the HPCs, the high-performance computing machines, then you also see that they have evolved with time because the workloads have evolved. So whereas we have done a lot of mathematical calculations for simulations of weather predictions, etc., simulations of how to damage cars, this was more like in the traditional modeling. But today we also have a lot of data, and we have to work with the data for artificial intelligence workloads. And therefore, this actually made this machine also combining the CPUs, the GPUs, and this enormous storage capability to work with workloads in the data. So data is king because we have a lot of workloads in the artificial intelligence area. So it's not only about bits, but it's also moving towards neurons to work with bits and neurons. Why? Because artificial neural networks is now coming to an age. We are using it for a lot of workloads already. And here you see a typical artificial neural network where you have the input layer, you have the neurons, you have the synapses in between, and then at the end you have your output to do classification and a lot of different things. This is an old technology. It has been actually invented in the 50s, but it hasn't been used. And why? Because it needs actually 3 different trends which have come together, which is the enormous amount of data which is available for training those neural networks, the compute power which enables us to calculate these deep neural nets, and also the development of algorithms. And all this has come together today that we can benefit and can really use those deep learning technologies. Here you see actually the ImageNet classification error as a function of year. And you also see here how dramatically this has, the error dramatically has been reduced. And if you look at it, you see this steep improvement, which actually has become true because of the introduction of deep neural networks. And today, the image classification is much better done by computers than by humans. And so there's a tremendous improvement, and as I mentioned, all this has become available because of algorithms, data, and compute power coming together. So in order to make further improvements, because we still use kind of narrow AI today, and to expand the capabilities of artificial intelligence, we have to continue improvements in compute power and also, of course, algorithms. This needs a lot of, today actually GPUs are typically used for artificial intelligence hardware. And you see here the performance as a function also again of the year. And we have benefited of kind of a 2.5 times improvement per year. However, GPU's performance is also leveling off. And the question is, how can we further improve the performance of compute power in order to enable the benefits which we're looking for in the artificial intelligence world? And therefore, we have worked in the recent years on how do we build new types of computers which can bring to bear this compute performance increase which we need. So how can we increase and improve the trend over the next couple of years? And so there are actually 3 solutions which we are pursuing. The first one is to use digital cores, so digital compute cores for artificial intelligence, but make use of approximate computing. The second one is using analog AI cores, so going to analog computing, and this has certain advantages which I will show you in a minute, and also use analog AI cores then with optimized devices. So go back to material science and find the best devices which you use in order to build those new types of computers. And just to show you the idea of approximate computing, the first type of solution is shown here. If you look at this picture here, although it's very pixelated, you immediately realize that this is Mona Lisa. So in order for you to process information, you don't need all the information to get the exact result. And the idea is done also when you go to these AI workloads, you can analyze at which stage you can reduce the precision in the calculation and can go from 64-bit down to lower number of bits for the calculation, which saves you actually a lot of energy and also increases the speed of your computation. So that's a basic idea behind. And we have done this, and actually last week at the NIPS conference, which is a high-level conference in the neural net area, we have actually demonstrated that we can do training with 4-bit and actually the 8-bit and 4-bit. And for inference, we can actually go down to 2-bit. And this opens up to increase the speed of those computations by a factor of 10 to 50. So we trade in this solution the numerical precision. So we are used to increasing in precision. And this is very important, don't get me wrong, to calculate your numbers on your bank account. But it's not so important for these workloads on artificial intelligence. So we trade numerical precision for computational efficiency in order to speed up the process. The next concept which we are pursuing is analog computing. And Sergey actually explained that in a typical computer, in a CPU, for Neumann computing, you have the logic part where you do the calculation, the processor part, and you also have the memory part. And in order to do the processing here, the logic calculation, you have to fetch your data, do the calculation, and store it back in your memory. And this costs a lot of energy and speed. And therefore, how can you speed up workloads without having this problem is shown here. So what we actually do is you want to calculate these deep neural networks, and for each of those calculations, you have to do a matrix calculation as shown here. You have your input, and you have your weights, which are stored in this matrix, and you do your calculation to have the output going to the next layer. And this calculation you can actually map on such a growth bar architecture where you apply the voltage here to each of those peripheral circuits. You have at each of those unit cells here, you have your weight stored. So your G11 would be stored in this cell, etc. And then you can use Ohm's law very simply and Kirchhoff's law to add up the current in the bottom here. So you can map your matrix multiplication, which you have to do many, many times in those neural nets, to such a simple circuit. And we can use at each of those unit cells here a memory device, a non-volatile memory device, where we can control the conductance. And for this, we can, for example, use here these type of phase change memory materials. I don't want to go more into detail, but it shows you that with this type of analog devices, you can do parallel computation, and you can gain a large performance increase by a factor of 1,000 to 10,000. And that's what we are currently pursuing. That's one solution, and the other solution is, as you have heard before, quantum computation. And what you see here is actually such a quantum computer. And you don't see the core, actually, but you only see the fridge to cool down the quantum computer. And so you need to the quantum computing happens at about 20 millikelvin. And here, this actually shows you the microwave frequency lines, which go down to the microprocessor, which is sitting here at the core. And such a microprocessor is shown here. We are using actually superconducting qubits for the quantum processor. And this is a chip where we have here like a superconducting qubit. These are the microwave lines to talk to the superconducting qubit. And here you see that these qubits actually behave like an artificial atom. And the superconducting qubit with a superconducting Josephson junction is a quantum information carrier. And with the microwave resonators, we can talk to those qubits. And Sergey has talked about the bits, the 1 and 0, and the difference in quantum computation is actually that you have a superposition of the 1s and 0s. So your qubit, your quantum bit, can be not only in 0 and the state 1, but it can be also in states in between. And this is illustrated by this so-called Bloch sphere, which means that your state can be actually take any state on the surface of the so-called sphere. And this leads to the fact that the performance of quantum computation is increasing by 2 to the power of n, where n is the number of qubits. And that's a secret, because if you add 1 additional qubit, then you actually double the performance of such a quantum computer. And this is different to classical computers, because in classical computation today, you have about 10 billion of transistors already in those integrated circuits. And if you add one additional transistor, it doesn't really matter. But in a quantum computer, if you add one additional qubit, it matters quite a bit, because you have, due to this exponential scaling, you double the performance of such a quantum computer. And so there are different layouts of devices which we have built. I don't want to go into detail, but this is our newest one. We have just released it in October. It's a 53-qubit system. And we have also opened the first quantum computer center in New York area, where we have actually 14 quantum computers available for commercial access. So I have to speed up a bit. I don't want to go too much into detail, but there are certain problems which are hard to be solved, and Sergey already has mentioned some of them. These are problems where the complexity increases exponentially, so-called many-body problems, for example, and they occur in material science and chemistry. Also, machine learning has advantages for quantum computing, and also in the area of optimization. So we are working on those examples, on finding and developing quantum algorithms, and we have demonstrated this already for calculating the states, also excited states of molecules, for optimization problems in the financial analysis, like quantum risk analysis, also for the dynamics of magnetic systems, and also in machine learning for classification. So there are many examples we're working right now on, and you see here that we are also developing the whole ecosystem around not only the hardware but also up to the software, that for the user it actually there's a seamless using the computer, so you don't have to worry about, you don't have to be a quantum physicist in order to use a quantum computer. So we are developing this Qiskit open source quantum computing framework, and we already have 160,000 users of it. We have done 16 million experiments, and we have actually opened up this quantum computer 3.5 years ago to the science community, or to everyone. So actually you can log in if you want and test and work on quantum computing and algorithms. And using our quantum computer, already 200 scientific papers have been written. And with this, I would like to close and say it's not only about bits anymore, it's about bits, neurons, and also quantum bits. And this we see as the future of computing. Thank you very much.
Thank you very much.